Hello, everyone. Very nice to have you all with us. So, in commenting on this year's split Nobel Prize in Physics, a piece in Quanta magazine concludes, aptly, I think, that the award to peoples is for work exploring the structure of the universe as a whole. Mayor and Kelow's, by contrast, found a Jupiter planet around the nearby stars. But these discoveries mark two profound shifts that have taken place over the past 50 years. The first is the creation of the first truly scientific and quantitative story of how we got here. The second is the stunning reconsideration of where exactly we are. On the latter end, we couldn't have planned today's installment of the Bellamy seminar series in the natural sciences better. In the sense that our speaker, Professor Alessandro Morbidelli, Morbi to his friends, will be addressing precisely that question, trying to ask about the special position of the solar system and the context of the galactic plethora of exoplanetary systems that followed this momentous discovery by Mayor and Kelos. Professor Morbidelli is a planetary scientist working for the CNRS at the Observatoire de la Côte d'Azur in Nice. With a mathematical background, he's an expert of planetary dynamics. He is known for his attempts to reconstruct the past history of the solar system and is now engaged in trying to explain the origin of the diverse architectures of observed planetary systems. In other words, he has spanned it all, and we could not have hoped for someone better to actually address the question that concerns us today. He has been the president of the Commission on Celestial Mechanics of the International Astronomical Union, director of the French Planetary Science Program, and member of the European Space Agency's Exoplanet Roadmap Advisory Team. He's an associate member of the Academies of Science in Belgium and France. Please help me give a warm welcome to Professor Morbidelli.
Thanks a lot, Jihad, for this very nice presentation. It's too kind, and thanks to all of you to come here so numerous. Thanks for the invitation. So, yeah, I would like to talk about planetary systems in the galaxy and our new perspective on the place of our solar system in the universe, which of course brings up this venerable question: is life common or rare in the universe? Are we alone or not in the universe? Of course, the idea that there can be planets everywhere and maybe life everywhere is not new. Already Giordano Bruno in the 16th century proposed this idea of the multiplicity of worlds. So imagine that every star we see in the sky is like a sun, and so like the sun is surrounded by a number of planets which, like the Earth, sustain life. Of course, it was a very dangerous idea to put forward at that time. As you all know, Giordano Bruno was burned as an heretic. Today it's easier to give this kind of talks. Lucky. So this discussion about the unicity of planets, of the Earth, and the unicity of life shifted suddenly from the philosophical domain to the scientific domain with the actual discovery of the first extrasolar planet, which, as Jihad remember, was done by two Swiss astronomers, Michel Mayor and Didier Queloz, in 1995, using a telescope, a French telescope, which is actually not very far from where I work. And for this reason, because this discovery really changed the course of planetary science, finally this year, Mayor and Queloz have been awarded the Nobel Prize of Physics. So what Mayor and Queloz discovered at the time was a Jupiter-mass planet around the 51st star of the Pegasus constellation. And that was already a first surprise, because this planet is not surprising by itself, as a Jovian mass and a structure more or less like Jupiter, but its position is very strange. Jupiter is quite far from the sun. It's at the distance that is 5 times the Earth-Sun distance, but this guy here, it's very close to its own star. It's about 1/10 of the Sun-Mercury distance, and actually the existence of giant planets so close to the star was not really expected. Today, so some 40 years later, we know something like 4,000 extrasolar planets and something like 700 multiplanetary systems. So actually, for the non-experts in the room, we'll just open a parenthesis on how we know the existence of planets. We typically don't see the extrasolar planets because the stars are bright and the planets are not bright. The planets don't produce light, they just reflect the light. So most planets the existence of most extrasolar planets is just deduced indirectly, but with a lot of confidence. One method, which is the one employed by Mayor and Kelos, is the one of radial velocity. So we typically say the planets turn around stars, but in reality, both the planet and the star turn around with the same orbital period around the common barycenter. So not only the planet moves, but also the star moves. And you don't see the planet because it's so faint compared to the star, but you can detect this movement of the star because as the star rotates around the common barycenter, sometimes it approaches you and sometimes it goes away from you. And this changes the wavelength of the light of the star due to the Doppler effect, which is the same process you have also in sounds. When an ambulance comes towards you, the tonality of the sound of the ambulance changes with respect to when the ambulance goes away. So by measuring this periodic shift of the starlight towards the blue and towards the red, one can measure the amplitude and the period of the star and then deduce that there is something that makes the star move around. And then one can compute the distance of the planet and the mass of the planet from the star. This is one method of detection and allows to determine the mass of the planet and the distance of the planet. There is another method, which is the one of eclipses. If you are lucky enough and the plane of the planet is on the line of sight on which you look at the star, every orbital period, the planet passes in front of the star and causes a dim eclipse. Very dim eclipse because, as in this diagram, the planet is much smaller than the star is. So it's not the star that disappears in the way. Its luminosity just becomes a little bit fainter by a millimagnitude or so. For observational astronomers, they know how a millimagnitude is tough to measure. But with today's instrumentation, this can be done, in particular from space, whereas radial velocity technique is mostly employed from the ground. This technique of detecting planets from eclipses is mostly conducted from space through dedicated space telescopes. Only in some special cases we can actually see the planets. These are giant planets, even super giant planets, so multiple times the mass of Jupiter, and which are located very far from the central star, so and the contrary of 51 Peg. So in this case, we can use new techniques of coronography, which actually shut off the light of the star at the center, and then we can see the lights from the planets rotating around the star. So this is a fantastic case of a star, the name is here, has 4 planets with masses between 5 and 10 Jupiter masses, where distances from 20 times the Earth-Sun distance, the astronomical unit, to 60 times. And what you see here, the dates, these numbers here are the dates at which the different pictures have been taken. So what you see here is not a computer animation. It's not a fake. This is a real planetary system that we see in motion, in rotation, which is quite mind-blowing if you think about it. We are looking at the planetary system as it turns around. So before going into a more in-depth discussion of what has been discovered with these 4,000 extrasolar planets and 700 multiplanetary systems, let's step back for a second and revisit our own solar system. Because our own solar system is characterized by some specific structures. So we have 8 planets rotating around the sun, and these planets can be grouped into 2 categories. Closer to the sun, we have the group of the terrestrial planets, which are small. The Earth is the biggest, or relatively small, and rocky. Even if we have an atmosphere, Venus has an atmosphere. In terms of total mass, it's totally negligible. And then further away, we have the realm of giant planets, which carry well their name, because their masses go from 300 Earth masses for Jupiter to 15 for Uranus. And these planets are not just much bigger than the terrestrial planets, they also have a different composition because they have a lot of gases, of primordial gases, hydrogen and helium, the same gases that make up the Sun. And for Jupiter and Saturn, actually most of the mass is due to hydrogen and helium surrounding a core of solids in a rocky and icy form. And all the planets have orbits which are almost circular, and all the planets lie almost on the same plane. And before the discovery of extrasolar planets, planetary scientists were thinking that every planetary system, more or less, should have looked like our own solar system. And of course, already the discovery of 51 Peg, so this giant planet situated at 1/10 of the star Mercury distance, destroyed that preconception. Today, 25 years afterwards, we can give a look at the census of extrasolar planets. And in this diagram, I show all the planets we know, more or less now, maybe a few more. And this diagram shows on the x-axis the distance of the planet from the central star, measured in astronomical units, which is the 150 million kilometers, this distance between the Earth and the Sun. And on the vertical axis, it's the mass of the planet normalized to the mass of the Earth. And in red here, you have our own planets on this diagram, so that you can compare in a glance the structure of the planets in our solar system and the structure of the planets that we find around other stars. So, as you can see immediately, the planets that we find around other stars tend to clump in three categories. There is this group, which is a group of that we call hot Jupiters, and because these are planets that have a mass comparable to the mass of Jupiter, if they take a factor of a few, but are much closer to the central star. As you can see, the distance is much less than the distance of Mercury from the star. So these planets are strongly irradiated from the central star, so they are actually physically hot. The temperature in the atmosphere can be thousands of degrees, and 51 Peg belongs to this group. Then we have a second group, which is that of warm Jupiters. Again, Jupiters, because the mass is about the same, or the order of Jupiter mass, so a few times more, but they are further away, so they are less irradiated by the stars, so certainly the temperature is less. But I catch your attention to the fact that even these planets are not really where Jupiter is, tend to be closer in. They typically have positions around 1 to a U, so they typically fill the positions that in our solar system is occupied by the terrestrial planets, not by the giant planets. And attends to the bias, because of course there are observational biases one has to take into account, attempts to debias the observed distribution, seems to show that the number of planets becomes more and more rare as we move out. Some planets are at the distance of Jupiter, but they are more of a minority. And if you go far enough, then we see the planets we can actually see directly by direct imaging, like those I showed before. And these are extremely rare. Despite of dedicated instruments built in the US and in Europe, just a handful of these planets have been found. The first group of planets is this one. It's called the super-Earths, are planets whose mass is in between the mass of the Earth and typically the mass of Uranus and Neptune, also much closer to the central star. Distance is comparable to that of a hot Jupiter, typically inward of the orbit of Mercury, sometimes reaching the orbit of Venus. You can see also a number of planets whose masses is smaller than the mass of the Earth, but these planets typically orbit stars which are less massive than the Sun. So in terms of relative mass ratio, they also qualify as super-Earths. And here, for comparison for scale, you see the planets of our solar system. So we see that where a lot of extrasolar planets lie in a part of the diagram where we don't have planets here in the solar system, and where we do have our own planets, we don't know extrasolar planets yet, except for Jupiter. But this may be just an observational bias. It's very difficult to see the analog of our planets around other stars. But the strange character of the extrasolar planets is not just due to their mass and distances. The giant planets around the stars are typically very eccentric. The eccentricity measures the shape of the orbit, as you can see in this diagram. If an orbit is circular, the eccentricity is 0. If an orbit is elliptical, the eccentricity is a number that is bigger and bigger the more elliptical the orbit is. And our own planet have eccentricities which are extremely close to 0. If you look at their orbit on a diagram, you would say this is a circle. You almost not notice that is weakly elliptical. And for a reason, because planets, as we will see, are born in a disk surrounding the star. So all planets should be born on circular coplanar orbit, and the solar system maintained that coplanarity and circular orbit. So it's an astonishment to see that extrasolar giant planets can have a wide range of orbital eccentricities, almost a uniform distribution, ranging from 0, a perfect circle, to 1, which is a second. In our solar system, only comets have such a large eccentricities. And actually, if you take the comet Gerasimov-Gerasimenko, the target of the Rosetta mission, and you plot it on this diagram, that's here, an eccentricity of 0.65 and the Sun galaxy of 3 AU. So what we see around other stars are giant planets on cometary orbits, which was totally unexpected and really surprising. The super-Earths in that respect are a little bit more normal. The super-Earths tend to come in groups, in systems. The giant planets around other stars tend to be low. And they have orbits which are rather circular and rather coplanar, and so similar to our solar terrestrial planet system in miniature. So this diagram, for instance, shows the system of Kepler-62, and it's a diagram at double scale. So the size of the planets drawn here, we don't have observations really of the physical properties of this planet, but it's drawn at scale with the sizes of the terrestrial planets of the solar system. So as you can see, these planets are a few times bigger than the Earth, so they take well the name super-Earth, except for this one, which is sort of super-Mars. And these orbits are at scale compared to the orbits of the terrestrial planets. So 3 of this 5-planet system, or 3 orbits of this 5-planet system lie well inside the orbit of Mercury, and the last 2 have an orbit comparable to Mercury and Venus. So what observations show us is that, despite the observational biases that certainly exist, is that 70% of the stars have planets that don't exist in the solar system, different from the planets of our own, hot Jupiters, warm Jupiters, eccentric Jupiters, super-Earths, and so on. And actually only 1% of solar-type stars have a planet like Jupiter on a Jupiter-like orbit, so quite far away and remaining on a circular orbit. So the observations tell us that our solar system is not typical. And it's at least a 1% level. 99% of the stars have something else, but maybe much less. And this is astonishing if you think about it. So this morning, we visited the Mineralogical Museum in Beirut, and the owner of the museum made a strong point in showing us a variety of crystals collected in different parts of the world, and pointing out that they are identical. And they are identical because the law of chemistry are universal. And so the same crystal formed in Afghanistan looks identical to the same crystal formed in Mexico. And but the law of physics are universal as well. So it's why it's not the same for planetary systems. Why the same law of physics don't form the same planetary systems over and over again around every star, like they form the same crystals over and over again in every continent. And so today, a major goal of planetary science is to understand the origin of the diversity of planetary systems. How it's possible that we get so many different structures, solar system and different extrasolar planetary systems out of the same kind of logic, the same laws of physics. And a side goal of this research is to try to have a sense of how rare is a planetary system like ours, because observations tell us it's at most 1%, but it could be much less. So we now guide you through a few basic ideas about how planets form, and trying to pinpoint a main driver of this diversity. So we think that planetary systems form around protoplanetary disks. When a star forms, initially, it has to be surrounded by a disk of gas and dust. This disk of gas and dust was deduced from mathematical considerations back in time by Laplace. And today, it's not a theory, it's a fact. We do see these planetary disks around young stars. Here, the only drawing is the star, but the disk is a picture. And the star has this jet, vertical jet, it's surrounded by a disk, exactly like in this scheme. So the star, the jet, and the disk. So the disk is made of gases and solids. And which solids exist depend on where we are in the disk. Because in the disk there is a gradient of temperature. It's hot closer to the star and it's cold further from the star. And so when it's very hot, only the most refractory elements can be in solid form. And when it's cold, also more volatile elements can be in solid form. In particular, there is a distance which actually moves over time. We can forget about that for the moment. Beyond which the temperature is small enough that water can be solid and is found in the disk in form of ice. Whereas closer to the sun than this line, the temperature is too high and water is in the form of vapor, and the only solids you can have to build your planets are silicates. Now, laboratory experiments show that ice is more sticky than silicates. And so we think that when this first dust, the solid dust in the disk starts to glue together using due to electrostatic forces, in the outer part where the water is in solid form, one can form aggregates that have a size of the order of centimeter to decimeter, which are actually have the structure of a sort of dirty snowball. So you have very small silicate grains entrained in an icy matrix. Now these grains, these bodies, because they are embedded in a disk which has a lot of gas, feel the friction of the gas, which slows down the body. And so they tend to drift towards the star, exactly like the artificial satellites when they pass through the high atmosphere, slow down, and they tend to fall on the Earth. So for instance, the International Space Station is falling on Earth because it's slowed down by the atmosphere, and it's periodically lifted up, otherwise it would fall on the Earth. So it's the same because of the friction from the gas in the disk, this aggregate drift towards the star. But by drifting towards the star, they leave the cold part of the disk, they pass through the snow line, and they penetrate into the warmer part of the disk. And when they do so, when they pass the snow line, the ice sublimates away, and this produces two effects. The first, half of the mass goes into the gas and will not be of any use anymore to make solid planets. But also, this dirty snowball will disintegrate in a collection of much smaller millimeter-sized silicate grains, so much smaller than the original parent aggregate. And this has a very important effect on planet formation. We think that planets mostly grow by accreting this dusty material that drifts through the disk. And so if you have two protoplanets sitting on these two sides of the snow line, they can grow very differently simply because this planet can see big dust aggregates due to ice and silicate, whereas this one can only see the small silicate grains. And actually, simulation that we have conducted a few years ago show that if you start from two protoplanets that have initially the same mass, half of the lunar mass, on both sides of the snow line, the planet beyond the snow line can grow to multiple Earth masses, 20 Earth masses, in the time when the inner one, because it can only accrete much smaller grains, which are much harder to capture for various hydrodynamical reasons, grows only to a mass comparable to the mass of Mars. So we think that in a general fashion, almost universally, because these properties of ice and so on are universal, so that the same as should happen everywhere around every star. At infancy, and during construction, a planetary system should have a sort of universal structure with small, rocky, silicate planets in the inner part, possibly of the order of the mass of Mars or so, that we call planetary embryos, and bigger bodies, multi-Earth mass objects, the mass of typical of super-Earths, beyond the snow line. And every star with a forming planetary system should have, at least temporarily, this structure. But then there is another aspect, which is universal as well. When the planets form, they're still embedded in the disk, and they interact with the disk through gravitational forces. And the result of this interaction is that the planets do not stay where they are, they migrate. And they typically migrate towards the central star, And the small planets don't migrate very much, but the multi-Earth planets do actually migrate. And so once the bigger planets grow beyond the snow line, they drift in. And by drifting in, they enter into the realm of the small silicate planetary embryos, and of course they cause a mess. And we do think that the migration and the fact that it brings planets from different places in the disk together, and some planets crossing the domain of other planets, is the mechanism by which most of the diversity we observe comes out. Actually, because a planet is encountering other planets, you have a phase of chaotic dynamics, and then it's well known in chaotic dynamics that even if you start with very similar initial conditions, you can end up with a great diversity of outcomes. And in order to illustrate that, I will show you now a few examples without any pretensions of covering all possibilities and solutions, just give you a few hints. So these are examples coming out of a number of numerical simulations of planetary evolutions that we have done in NIS. So I will show all the animations I will show taken from the simulations are shown with the same kind of diagrams so that you don't have to, it doesn't become too complicated. So we will see the evolution of the protoplanets in a diagram where this axis is the distance from the star in astronomical units. This axis is the orbital eccentricity that you know is related to the shape of the orbit. The colors denote the masses of the planet, so as the planet grows, they will change of colors. So at some location we have the snow line, and here we will have the time of the simulation as it passes. This triangle in these coordinates doesn't have much sense, but it's there just to remind you that we are talking still of an early phase where the sun, during which the star is surrounded by a protoplanetary disk of gas, which disappears only after 5–10 million years. But you can also imagine that you're looking at the system, the evolution of the system edge on, in which sense that the disk would have this kind of shape. So as I said before, we expect that the biggest planets grow beyond the snow line, because that's where you have ice available and big grains available for growth, but they migrate. So in the most general case, what do we expect? We expect that all these bodies migrate in. Sometimes migration is reversed, but only temporarily. And during migration, planets can merge together and grow, so their color changes. And migration keeps going until the planets reach the inner edge of the disk. The disk does not extend all the way to the star, but because of magnetic effect, it's truncated very close to the star at about 1/10 or a few hundredths of an astronomical unit. And because migration is driven by the disk, when the planets reach the edge of the disk, they stop it. And so the planets accumulate there. There is not enough space for everybody. So they keep colliding with each other, growing. So you see the colors are changing until they reach a small enough number to acquire a stable configuration or a temporarily stable configuration. So this kind of evolution, as you can see, brings planets to acquire a few times the mass of the Earth, maybe up to 15 times the mass of the Earth, and park themselves very close to the central star. So we think this is the main mechanism by which close-in super-Earths come out to be. But as I showed at the beginning, not all stars have close-in super-Earths. The sun, for instance, doesn't have close-in super-Earths. So, and only 50% of the stars have close-in super-Earths. So what else can happen so that this kind of dynamics does not occur and the planets don't rush all to the inner edge of the disk? Well, a possibility is this one. The possibility is that the innermost of these super-Earth planets formed beyond the snow line grows a little bit bigger and starts to accrete gas, the gas from the disk, hydrogen and helium. And by piling up enough mass of hydrogen and helium in their atmosphere, it becomes a giant planet like Jupiter. Now, a giant planet migrates also, but less fast than the super-Earths. And typically during the lifetime of the disk, 5 million years, its migration is enough to bring it into the warm Jupiter region, 1,2 AU, but not all the way to the inner edge of the disk. And so if we enact that, so we assume that the first of the super-Earths become a giant planet and we enact its slower migration, this is what we see. the super Earth behind it would like to migrate faster to go to the inner edge of the disk. But to do so, they have to pass through the orbit of the giant planet, which is not an easy task to do. It's like when you're driving a car and you have a truck in front of you. It's not easy to overtake the truck. You can manage, but not so probable. So the same is that these super Earth planets would like to pass, overtake the Jupiter and go to the inner edge of the disk. But in most cases, they are confined behind the giant planet. And then again, there is not enough space for them. They collide with each other. Their number decreases. And at the end, we have a group of super Earth planets, but they are behind the giant planet and close to the star. There is nothing. So in this case, we have not produced a close-in super Earths because a giant planet, a Jupiter mass planet, has provided an effective barrier to their migration. So this starts to look like a little bit like our solar system, right? We have a giant planet, we have big planets behind Jupiter, we have no close-in super Earths. But it's not the solar system, because in this case, the giant planet is in the terrestrial planet region, 1 to AU. So our Jupiter is much further away. So what actually happened in the solar system? We think that in the solar system, not just the first of the innermost super Earths became a giant planet, became Jupiter, but also the second one started to accrete gas and develop a massive atmosphere to become Saturn. And hydrodynamical simulations show that Jupiter and Saturn are such that, mass ratio such that their combined gravitational forces prevent their inward migration. If anything, they migrate somewhat outwards. And by the little story, we now know 2 giant planets embedded in a disk, because most of the extrasolar planets we find are billions of years old, so the disk has gone. But now we have found 2 giant planets in a disk around the star PDS 70, and they are 3 Jupiter masses and 1 Jupiter mass, so the same mass ratio in Jupiter and Saturn, and they also seem to be not in inward migration from what we can deduce from the structure of the disk. Okay, this was just a parenthesis. So what happens in this case? We have Jupiter and Saturn will not migrate into the terrestrial planet region. We stay more or less in place. And all the super Earths behind, like before, will try to pass. And now you don't have 1 truck to overtake. You have 2 trucks. That's almost impossible. So they stay behind, they pile up, they collide with each other, they grow. And if we wait enough, we see further collisions of these protoplanets to form at the end 2 planets of 15 Earth masses like Uranus and Neptune. This is going to happen very, very, very soon. So you see, sometimes the planets can stay stable for a while, and then they develop an instability, and there are new collisions, and you are left with fewer planets and of bigger masses. So we think this is actually what happened in the solar system, and this is actually a good model for the formation of Uranus and Neptune. Because Uranus and Neptune are characterized by a very odd property. The spin axis of these planets is very inclined with respect to the orbit of the planet. For Uranus, it's even inclined by 98 degrees, and for Neptune, 30 degrees. And we don't have an explanation for this big tilt of the spin axis other than these planets have been involved in giant collisions with other planets. Also, Saturn is inclined, you see, almost like Neptune. But for Saturn, we know this explanation. It's a subtle dynamical process that has been understood. But for Uranus and Neptune, there are no subtle dynamical processes found of today. And so people think that this big obliquity is due to collisions, that due to the fact that Uranus and Neptune grew through giant impacts. And this kind of dynamics that we've seen when we start from a system of super Earths or 3-5 Earth masses, and that then collide with each other because their migration route is barred by Jupiter and Saturn, does produce planets with the masses of Uranus and Neptune at the end through a series of giant impacts, which then explains why we have these odd obliquities. So if what I said is correct, and honestly, we are not sure, it's a possibility, it's a model, then we do predict, we do expect that there is an anti-correlation between the presence of giant planets and presence of close-in super Earths. So if we see a star which has close-in super Earths, we expect that there is no giant planet beyond, because the giant planet would have prevented their migration close to the star. And if we see nothing close to the star, then maybe there is a giant planet beyond that, like our own Jupiter, kept the other super Earths behind its orbit. Now, the existence of this correlation is very debated by observers, and we have papers in the literature arguing both ways. So this is really a problem, an open problem, how often this we can categorize a planetary system in one of these two categories. And if we see many, so if we find that there are several giant planets when we have closing super Earths, it means the giant planets are not the closest body, bigger body to form. But in the solar system, this is most likely what happened. And for that reason, these small silicate planetary embryos that I talked before, that formed within the snow line, remain there, protected, because Jupiter protected them from the migration of the bigger planets. And then these small planetary embryos on a longer time scale, once the disk disappeared, could eventually form the terrestrial planets like the Earth. But this is not the entire story, because as I showed you before, there is another oddity of giant planets, the fact that they are not circular, but they have very large eccentricities. It's quite a consensus in the community that because all planets are born on circular orbits, I think we are sure of that, these eccentricities come because giant planet systems, after their formation and after gas removal, typically become unstable. This has been illustrated by a number of people, and I will borrow a simulation from a colleague, an American colleague working in Bordeaux. So we have a star, the protoplanetary disk, and we have the formation of a number of giant planets. And after the disappearance of the disk, if you simulate on the dynamics on a longer time scale, you find that very often, after tens of millions of years, the giant planets become unstable. Here you see the small planetary embryos that are trying to form terrestrial planets, but at some point the giant planet become unstable, and this is what you get. The innermost giant planet is kicked in, and its orbit is not circular anymore, as an eccentricity of order of 0.3, 0.4. One planet has been ejected from the system in interstellar space. One planet has been ejected on a very distant orbit, also very eccentric, could be one of the planets we can image directly. And as you can see, and you have seen, all these silicate protoplanets that were in the process of forming terrestrial planets have all disappeared, because as soon as a giant planet becomes eccentric, all the terrestrial planets have to become eccentric and tend to fall onto the central star. So luckily, this didn't happen to our solar system. Otherwise, it would not be here. But actually, we do think that also the giant planets in our solar system passed through a phase of dynamical instability. Why do we think so? We think so because the simulations of the dynamics of the giant planets in the disk of gas, like the one I showed before, that was forming Uranus and Neptune, leave you at the end with the four giant planets that are extraordinarily close to each other. Jupiter is maybe at 5 AU, but Saturn, Uranus, and Neptune are very close to each other. They all are within 12 AU. And this is because of migration, that in the disk brings all the planets against each other, close to each other. But this is not the distribution, orbital distribution of the giant planets that we have today. The giant planets today are not on this kind of orbits, are on this kind of orbits. The planets are much more separated. Uranus is around 20 AU, Neptune is around 30 AU, Saturn is around 10 AU. So if this result is correct, we need to find a process that is capable of transforming the orbit of the giant planets from these pristine ones on which they formed during the gas disk phase to the current ones. And we think that the dynamical instability is this process. And this is a model being developed in NICE, is often called the NICE model, went through a number of modifications and refinement. But basically the idea is that at the end of the gas disk phase, so when the planets were much closer to each other, there was a disk of smaller bodies of planetesimals beyond the Neptune, the ancestor of what we call today the Kuiper belt. And the dynamical interactions between the planet and the planetesimals slowly modify the planetesimal disk and modify the giant planet orbits. And so after some time, which can be very long or very short, depending on the separation between the disk and Neptune, the giant planet became unstable. And when this happens, this simulation of 720 million years, the giant planets cannot stay so close to each other. They spread. they separate. And this brings Saturn at 10 AU and Uranus at 20 and Neptune at 30 AU, like the planets that are today in our solar system, and gives some small eccentricity to Jupiter and Saturn, although not very much. So we really think this happened. We don't know when it happened, if it happened early or late, but we really think this happened because it left a lot of traces in the fine structure of the outer solar system, the Kuiper belt, the Oort cloud, the satellite population, the Trojans, and so on. And there is no other comprehensive model explaining all these structures other than the giant planet instability. You can argue on detail of what the planets actually did, but the instability is now a well-established fact. But now you should be very confused, right? Because I told you before that giant planets, when they become unstable, they become very eccentric. Now I told you that I told you from the beginning, our giant planets are almost circular. Now I tell you that also our giant planets came through a phase of instability. So why are not so eccentric? Why are they not so eccentric? Well, in the simulations that work, that reproduce the solar system, what happens is that during the instabilities, the planets encounter with each other, but by chance, and I stress chance, Jupiter and Saturn don't have close encounter with each other. In that case, we reproduce well the solar system, and Jupiter at the end, if there are no encounters with Saturn, has an orbit with a small eccentricity. But there are a number of other simulations in which during the instability phase, Jupiter and Saturn encounter with each other. These simulations fail in terms of reconstructing the solar system because the outer solar system blows apart. Uranus and Neptune are ejected, and often even Saturn are ejected, but Jupiter becomes very eccentric, of the order of an eccentricity of 0.4, 0.5, very comparable, as you can see, with the eccentricities of the worn Jupiters that are here illustrated by red dots, the size of the dot being proportional to the size of Jupiter, with Jupiter at scale. So if I can to summarize what I said so far, the laws of physics are universal. We are not putting that in discussion, of course. And there are basic processes that rule planet formations everywhere. The fact that planets grow by process that we call pebble accretion, the accretion of drifting dust. The fact that planet migrates. The fact that planets tend to become unstable after the disappearance of the gas. And migration in particular introduces a lot of variability in the final outcomes, introduces a phase of chaotic dynamics, and chaotic dynamics is very known to lead to a diversity of outcomes, even starting from very close initial conditions. If we understand the history of the solar system, and then the specific structure of the solar system is related to the chain of 3 fortuitous events. The first one is that of the big planets formed beyond the snow line, the innermost one started to capture gas and become a giant planet. That was Jupiter. Without Jupiter, Uranus and Neptune, or their precursors, would have migrated all the way towards the sun, swiping away all the material through the terrestrial planet region. It would not be here. But also, behind Jupiter, the formation of Saturn followed. And that was a blessing because they stopped the migration of Jupiter. Otherwise, Jupiter would have migrated into the warm Jupiter region, would have migrated to the place of the Earth. And then there would not have been space for the Earth to form. And finally, when the gas disappeared, although our giant planets entered into the phase of instability, by chance, Jupiter and Saturn avoided encountering each other. Otherwise, Jupiter would have become very eccentric, and the Earth would have been thrown into the sun. So we're not really able to quantify the probability of each of these events happening and happening in a good sequence. But this suggests, at least to me, that our solar system should be really rare, even much more rare than the 1% upper bound that the simulations suggest. But of course, we need to live in a system that allows the formation of a habitable planet like the Earth, however improbable it is. But at this point, you may object. You may say, well, you're too much anthropocentric. So you're looking for a habitable planet that looks like the Earth. So in a planetary system, it looks like the solar system. What about possibility of forming life on more exotic worlds? And this is a very valid objection. So I think I should say a few words about that. In particular, astronomers, of course, who ultimately look for the answer these questions, are we alone in the universe, have carefully looked at the possibility of having life sustained on planets different from the Earth, in systems different from the solar system. And the best candidates are considered to be the super Earths. So to be host life, biologists tell us that life needs liquid water. And so the planet has to be in a position so that it's not too warm and not too cold, so that the water can stay liquid at the surface of the planet. If the planet is too close to the star, the water will evaporate, like has been the case for Venus probably. And if it is too far away, the ice freezes out, which is probably the case of Mars. You need to be at the right middle to have a good temperature like the Earth. Now, this distance at which a planet has to be in order to sustain liquid water at the surface and be habitable, so the astronomers call habitable zone the zone where the planet can have liquid water and nothing else. So this distance depends on the kind of star you are orbiting around, because if you are orbiting around a massive star, which is very bright and very hot, you need to be very far away to have a mild temperature. But if you are orbiting a small star, which is very thin, then you have to be close in to have a mild temperature, because if you are at the distance of the Earth, it's then cold. And the super Earths that we are finding, so very close to the central star, are clearly too hot around solar type stars, but are exactly the right distance around the small mass stars. So super Earths around the small mass stars are often in the habitable zone, and we know plenty of the super Earths around small mass stars in the habitable zone, which so in first sight like seem to be the best candidate to be habitable worlds. For instance, the TRAPPIST-1 system, a fantastic system of 7 planets found by Belgian colleagues orbiting a star which is 8% of the mass of the Sun. So in this drawing, the planets are drawn to scale compared to the terrestrial planets of the solar system. So there are 7 planets of the size of the Earth, basically. They are super Earths because the central star is small in terms of mass ratio. The orbits are not drawn to scale. The orbits are all down here. So this upper plot is magnified 25 times because the system is so tiny. But the central star is so dim that actually 3 planets, E, F, and G, are in the so-called habitable zone where liquid water could be at their surface. So unlike the solar system, there we could have life on multiple planets. So you can imagine transplanetary trips or something very exotic and very fascinating. You take the closest star to us, Proxima Centauri. Proxima Centauri, 4 light years away from the Sun. It's also a small star, a fraction of the solar mass. It also has a super Earth in the habitable zone. And it's not so far away. You could even conceive of sending some probe there one day. People are thinking seriously about nanosatellites pushed by laser beams to a speed of about half the speed of light, so that they could reach the planet in about 10 years and have a very quick flight by. So these super Earths around us in the habitable zone around small stars are more or less everywhere. So, but are they really habitable? And there are a number of problems that should be sorted out by scientists. So I will just tell what the problems are without having the pretension to say that any of this is a fatal problem. But there are some number of problems to think about. So first of all, if a planet is very close to the central star, it undergoes strong tides. And as a consequence of the strong tides, the planet always should show the same face to the star, like the moon always shows the same face to the Earth. So it's true that on average, the planet has a mild temperature, but in reality, there is one hemisphere which is hot because it faces the star. One hemisphere, it's in the eternal darkness, so it's very cold. If there is an atmosphere with strong winds, of course, the temperature can be homogenized, but then you expect strong winds, so probably living forms are not very high above the ground. We don't know, but that's certainly something exotic compared to the climate of the Earth. You should also keep in mind that small stars, despite they are not very energetic in terms of light or in the visible spectrum, they are very active in the X-ray and the UV part of the spectrum. And for our own life, based on ADN, these radiations are very dangerous because they induce mutations. So, and then errors in the genetic transcription. So what are the consequences of life on these planets which are so heavily bombarded by X-rays? I said before that you need to have water, liquid water, to sustain life. So without any water, you don't have any life. And well, we don't know if these planets have some water or not. But what is less known is that too much water can cause a problem. So for the on the Earth, you think we have a lot of water because you look around at the bay and there is a lot of water. But in reality, the amount of water on Earth is tiny. It's only 0.02% of the mass of the Earth. And most of this water is just in a thin veneer on the crust of the Earth. And we have a planet with a core, a mantle, and a crust, and then the ocean, which is on average just a few kilometers thick. So if you have a super Earth, and the super Earth has some water, but not too much, say less than 1% of the mass, total mass of the planet, we do expect it's about the same. The super Earth should have a surface ocean. But if it has more, few percent of the total mass of the Earth, the planet in water, then there is a problem. The problem is that the ocean becomes too deep. And so the pressure at the base of the ocean becomes enormous. And if you compress water too much, it freezes out. There are two kinds of ices that you can produce. You can produce ices by cooling the water, as you do in your refrigerator, and then the ice is light and floats. But you can also produce ice by compressing the water, which you cannot do at home with huge pressure. In that case, the ice is dense and sinks. And so around the super Earth, which already has a lot of gravity, if you have a lot of water, you expect maybe a liquid surface, a liquid ocean if you are in the habitable zone, but underneath a high pressure ice shell. And this may be a problem because to sustain life, you don't just need water, you also need nutrients in the water. And on Earth, these nutrients are due to the erosion of the continental shelf and the bottom of the oceans. But if you have a deep ice sheet, it's not clear where these nutrients would come from. Maybe just from meteorites falling in the ocean. We don't know, but it can be less trivial than we think. And last but not least, we know now by observations that most habitable super Earths have actually hydrogen and helium atmospheres. Because by comparing the mass of the planet to the radius of the planet, we can get a sense of the global structure of the planet. For instance, the habitable super Earths in the TRAPPIST system have an atmosphere of hydrogen and helium. So they actually have a structure which is similar to that of Neptune, with a core and a mantle and a hydrogen and helium atmosphere. Maybe they have a water ocean, okay, on the surface, but they have this hydrogen and helium atmosphere. Is this good? Is this bad for life? Well, I mean, by itself, hydrogen is not bad for life, but the most sophisticated form of life on Earth use oxygen for cell respiration, and also for our own respiration, but even just cells. Even plants undergo cell respiration. And only very simple bacteria, like cyanobacteria, don't use oxygen at all. And oxygen on the Earth is a biological product. At the beginning, there was very little oxygen in the atmosphere, and then the cyanobacteria produced oxygen, polluted the atmosphere on the Earth, which is dominated by nitrogen, with oxygen, died because of that, but the oxygen was a chance for living forms to develop. In a super Earth like that, with a hydrogen atmosphere, it's impossible to put oxygen in the atmosphere. Even if you have an ocean and cyanobacteria in the ocean that produce by photosynthesis oxygen, as soon as the oxygen is liberated in the atmosphere, combines with the hydrogen, it's an extremely strong reaction and makes water. So these atmospheres will never be oxygenated, and so life doesn't have an efficient form of energy, like combustion, to develop. So we can have life, but very simple life, nothing like the living forms we are used to. So in conclusions, how generic is life? And the answer can only be, we don't know. And but what we do know is that solar system analogs are rare. Observationally, it's at most 1% of the stars. Probably if we understand how the solar system came out with its structure, it's much less, but that's a model. So take 1% as an upper bound. Then the second question is, can Earth-like planets exist in a planetary system that is different from the solar system? I tend to think, well, the answer is we don't know. So I think I'm pretty confident that if in our solar system Jupiter had not formed, we would not be here. But then you can imagine that a star is surrounded by a disk, a small disk with not much mass, so can only produce small planets, and one of these planets is more or less like the Earth. That's a possibility. We don't really know. You should be aware and be skeptical of the frequent media announcements of having found a habitable super-Earths. Habitable super-Earths are just planets at the right distance from the central star to sustain liquid water in their surface. But as I showed to you, there are plenty of problems about life in these super-Earths close to low-mass stars. And we don't know if actually any of them is a good planet host candidate. There may be other exotic worlds which are more favorable for developing life. I think one of those are the satellites of giant planets in the habitable zone. And I showed you there are many giant planets in the habitable zone, the warm Jupiters, that are typically at distances typical of the Earth from the Sun around the solar mass stars. So this may be good not planets, they are satellites, but it could be good worlds to host life. And so because astronomers don't just do simulations and calculations, but also like to dream sometimes, then I will leave you with this picture, the drawing, of course, and I thank you for your attention.
Thank you very much, Morbi. Now we can safely add your skills as a storyteller to all the other skills that you shared with us. So we have time for questions, of course, and I'm expecting a lot from our audience, and I will then circulate the microphone so you can ask it in a way that everyone else can hear it. Yes?
Thank you for your talk. It was really interesting. I have just one question. How can planets come closer to a specific star to how you presented it at 0.1 AU and then stay there? If they're getting closer, shouldn't they like enter the star?
So the migration occurs because of gravitational perturbations between the planet and the disk. Because when the planet starts to have enough gravity, enough mass, like an Earth mass planet, it starts to perturb the distribution of gas in the disk. So the disk loses its symmetry, and there are some overdense region of gas that form near the planet. And then these overdense regions of gas exert forces on the planet, and one can show mathematically and also through simulations that these forces slow down the planet and so make it migrate through the disk. This is called planet migration. It's a new process. It was envisioned actually in the 80s, but it looked crazy because in our solar system, the planets are far away. So sort of put aside until Major and Queloz found these giant planets so close to the star, and then the idea of planet migration has been resurrected and intensively studied, and there is no doubt that planets do migrate in disks. Why do they stop? Because the disk is not extended all the way to the star. The star is, particularly young stars, are very magnetically active. So, and there is a magnetic coupling between the magnetic field of the star and the gas in the disk, which is close to the star, is hot enough to be ionized. And this changes the dynamics of the disk and basically truncates the disk. So if the medium, so the disk is what driving migration, and if the disk ends here, your migration can continue only as long as you are in the disk. Once the disk stops, your migration has to stop there. There are actually some restoring forces occurring at the edge. So even if another planet comes behind and tries to push you beyond, throw you off the cliff, there are actually some restoring forces that keep the planet at the disk. Then, of course, it's a little bit mathematically complicated. You don't want to enter any technicality, of course, a lot in just a few slides. But all these forces are actually implemented in the simulations I showed to you. And so that's what happens. There is a specific part in place in every disk.
I have two questions. The first one, we know by the gravitational field because planets are within the gravitational field of the sun. What happens if if there is another huge or massive star? We know that all planets are traveling through space; they are not static. So, what happens if our sun reached or enters another field of massive gravitation of a massive star? And the second question, based on what the planets in our solar system are arranged, based on the mass away from the sun, based on density, based on what?
Okay,
Thank
so all the simulations I showed will concern the planets around a single star, but many stars in the galaxy are binary stars and even triples, and you don't talk about it at all about formation of stars around the binaries. But observations, also theoretical studies, have focused on that. And there are planets around binary stars. So there are typically three kinds of binaries. There are binaries where the stars are very close to each other. In that case, the planets are found around both of the stars. So instead of turning around the sun, turn around two suns. Then you have binaries which are well separated from each other, and then you can find planets around each of the stars, like satellites of like the satellites of the giant planets. You can think of the Sun-Jupiter system as a binary star, and the satellites of Jupiter like the planets of the secondary star. And then there are stars whose separation is of the order of 10 AU or so, and these are the worst ones. There are some planets, but are very rare, and that's because in that case, the star is where the planets would like to form, and so that's a mess, and they tend to be no planets. The solar system, the sun forms in clusters typically, and then these clusters separate when the gas goes away because the gravitational potential of the gas goes away. So the sun most likely formed in a star cluster as well. By looking at the structure of the distant solar system, we can put some boundaries on how close ever on the history of the solar system we had stellar encounters. And it seems that very early on, when the planets were forming, probably we had a stellar encounter at about 1,000 AU or so, 1,000 times the Earth-Sun distance. And that's because some objects, distant objects, are decoupled from Neptune. So you like Sedna, if you are familiar with that object, to produce the orbit of Sedna, you need an encounter of a star about 1,000 AU. But then once the disk around the sun disappeared and the giant planet became unstable, at that point, the sun had to be outside of the cluster, and we never had since any encounter with a massive star within a few tens of thousands of astronomical units. Otherwise, we would have lost the Oort cloud. And the Oort cloud was formed during the giant planet instability and the speed day. So the galaxy is pretty, there are 100 billion stars, but there is a huge volume. So close encounters are very, very rare. And the odds are that the sun will never encounter a star closer than that distance, at least a massive one. So about the ranging of our solar planets, well, they are what they are, right? So my beginning was that it's clearly we have a sorting in terms of masses and compositions. Inner planets are small and rocky, and outer planets are big in terms of mass, at least 15 Earth masses, going up to 300, and contain a lot of gas and primordial gas, not gas without gas from the rocks, but the gas that form the sun, so the gas from the disk. And so the planets that have this gas must have formed within the protoplanetary disk, must have formed within a few million years. All the giant planets formed within a few million years. The planets that instead, like the Earth, don't have hydrogen and helium may have taken much longer to form. And indeed, radioactive chronometers suggest that the Earth took about 100 millions of years to form. So the Earth completed its formation well after that the hydrogen and helium has been removed from the sun disk. Yes.
Thank you for a good talk. I read somewhere that another condition for a habitable planet is that it should have a giant planet outside it that will act like a vacuum cleaner, protecting it from all asteroids, comets, and runaway satellites. What can you tell us about
this? This is an old idea coming from a great scientist called George Weatherly, who did a big part of the history of planetary science. It has been a little bit reconsidered, because it's true that in our solar system, if you don't have Jupiter, in principle, you could have a higher flux of comets bombarding the Earth. But if you don't have Jupiter, you have a totally different planetary system. So maybe you don't even have comets coming into the planetary system. But I reached here the same conclusion, right? But from different grounds. So without Jupiter, you have migration. And then you have these super Earths forming a snow line, migrating in, and taking away all the material from the inner solar system. So you can form terrestrial planets. So I think Jupiter is necessary to block migration in the most favorable condition and protect the inner solar system from invasion. Then the Earth can form. The only alternative would be a very low mass disk, where nothing very big can develop, and then you form the Earth in situ from the little mass you have. But if you have a sort of massive disk, like the Sun clearly had, to form this giant planet, but you don't form Jupiter, then we are doomed by the migration of Uranus and Neptune and its precursors.
Thank you again for the presentation. My question is, the planet that collided with Earth that basically formed the moon, I think it's called Theia, is it basically also due to planetary migration? Like, is it in any way related to?
It's too late for planet migration. Planet migration occurs when there is the gas around the star. The gas goes away in 5-10 million years. The moon forming event is dated to be 50 to 100 million years. So it's too late. So in all evidence, the solar system was trying to form a system of 5 terrestrial planets, and that system became unstable. It's an interesting possibility that the system became unstable because the giant planet became unstable. So we have to place this giant planet instability sometime. We don't know when. It's very hard. We thought at some point to have understood the giant planet instability is associated to a specific time in the solar system. It's probably not true. So now we don't know when it happened. Possibility is that, the instability from the giant planet system triggered an instability in a 5 terrestrial planet system, leading to this giant impact. It's just a possibility.
Sure.
Hello, thank you for that beautiful talk. And I have a problem with the definition of a habitable zone. I think it's too basic at the moment, because we're just looking at water, and if you leave a cup of water for thousands and millions of years just isolated at one point, it will never have life. So is there a possibility in the near future to tweak this definition and maybe add, for example, the formation of hydrogen cyanide as an extra condition or criteria to have a habitable zone, where hydrogen cyanide has been recently proven to form nucleic acids, lipids, and proteins under UV light?
Yeah, you're absolutely right. So the habitable zone concept is a necessary concept. So you want to have liquid water, but liquid water is not enough. And I gave you plenty of examples of problems that may exist. And in addition, you need organic chemistry, you need the favorable conditions to turn organic chemistry into life, which is a whole kind of problems. I'm not a biologist. So the reasons for which astronomers focus on the habitable zone is that it's simple. So it's relatively simple to estimate the temperature of a planet, to measure the temperature of a planet. Then if you invoke, do I have some specific organic molecules or not, how can you tell? Observation with today's technology. So that's why we are limited at that stage so far, but in the future, astronomers plan to go beyond. So now there is, after discovering so many planets, we are now reaching the point that we don't care discovering many more planets, but we care in characterizing them. And so after the last generation of space telescopes looking for analogs of Earths, So Earth mass planets at 1 AU from a solar-like star with TESS and Plato, and NASA and ESA. Then the next generation in the roadmap is to have a set of instruments to characterize the chemistry of the atmosphere of these planets. And then we can start to say, this planet has hydrogen and helium, so forget about complicated form of life. This planet has ozone, so it must have a lot of oxygen, so maybe something we're producing that. Then we will try in the future, and then that's further away down the road, to have direct imaging of planets in the habitable zone, and then you can do direct spectroscopy. And in principle, you could even imagine to observe the chlorophyll lines, spectral lines, because they can be observed. There are tests in looking at the radiation of the light reflected by the Earth off the moon, and you can see the chlorophyll lines. So in principle, if you can do direct spectroscopy of planets, at some point you will be able to detect vegetables in the existing plants. So clearly, we will go beyond this simple definition of our habitable zone and try to characterize of all these potentially habitable planets, characterize those which don't look good, and those which look much better, and focus more and more on the most promising target. This will take decades. So already the characterization of the atmospheres, we start with JWST, James Webb Space Telescope, which will be launched in a few years. Then we have to wait for the telescope of the European Space Agency, which will fly in 2035. And then for direct imaging, we need the super fancy interferometers, which are still at the level of technological developments that are not ready to be deployed in space. But eventually, this will be done. So by I think the end of the century, for sure, maybe even 2050, we will start to have a deep characterization of these potentially habitable planets. I like them to call them potentially habitable planets because it's just a necessary condition, not a sufficient condition by far.
Thank you so much.
Thank you. A question about the spatial orientation. Those observations and findings, please, do they relate mostly to our own Milky Way, or do they span out the universe from other galaxies as well?
No, they only concern our own Milky Way, and actually even probe just the zone of the Milky Way, because then the stars become very distant and faint, and it's difficult to track them with enough precision to detect planets, with one exception. It's the planets detected by a technique called microlensing. And it's a technique, it's due to the deflection of light by gravitational bodies with some mass. And this technique is very efficient if you look towards the galactic bulge, galactic center. And then you can detect planets around stars which are much close, they are between the sun and the galactic center. And so it's very interesting by itself. And actually it seems that there is, recently, people have started to do some analysis of all these planets detected by microlensing, and curiously enough, they are all in a narrow range of distances from the galactic center. So there seems to be a sort of preferential zone in the galaxy between the sun and the galactic center, where most of these planets detected by microlensing are. So these are very exotic planets around very exotic stars. Otherwise, most of what we know, I showed in my diagrams for radial velocity direct imaging in transit, are just in the solar neighborhood, some 100 light years away, typically.
I have room for one more question. Okay, we have to be mindful. So, we're out of a week of consideration of the special conditions that led to the formation of Earth's moon. Yeah, so we're out of a week that was dedicated to the special conditions that led to the formation of Earth's very special companion, even by solar system standards. So I wonder if you can review for our audience the state of thinking, observations, planned observations pertaining to exomoons, moons around planets, in the context of a picture where migration is fairly common, instabilities are common. If you can discuss the survival of exomoons in that framework, and their detectability?
Yeah. So, well, there are two kinds of moons in the solar system. There are the moons of the terrestrial planets and the moons of the giant planets. So the Earth has a sizable moon, the only terrestrial planet to have it. So we don't know how generic a moon is. Venus doesn't have any. Mars has two little stones around it. They only qualify for moons. Mercury has no moon. So we really don't know how what to expect for moons of Earth-like planets or super Earths. But giant planets, all the giant planets in our solar system have many satellites, because when a giant planet forms, because it accretes the gas, it forms a circumplanetary disk, analog to the protoplanetary disk around the stars. So the story repeats again, and like planets form around stars, satellites form around giant planets. So giant planets, satellites of giant planets should be ubiquitous, and giant planets, we've seen, they're fairly numerous. Now, the giant planets migrate, and giant planets become eccentric. So when they become eccentric because of close encounters with other planets. That's very bad for satellite stability. Even in our solar system, so we worried in our simulations of the NIST model about the actual distance between the encounters between the planets to be sure that the satellites that we know of would survive. And they survive in most of the cases because the specific instability we had in the solar system was very weak. And that's why Jupiter is on a quasi-circular orbit. But if you take a strong instability like the one that my friend Sean Raymond simulated, so I show it again here, then you have really close encounters between close-by planets, and it's very likely that the entire satellite system will be destroyed. So you have to look at the planets that kept the most mild orbits, most likely. And then they migrate, and by migration, of course, the regional stability of the satellite around the planet shrinks. And so you may have satellites that were stable when the planet is at the snow line and become unstable when the planet comes too close to the sun. But if you stick to warm Jupiters in the habitable zone, it's not such a dramatic effect. It's just a factor of 3 to 5 in the scaling. So we do expect to find moons also around the most circular warm Jupiters, at least. Possibly not the hot Jupiters, possibly not the eccentric Jupiters. Observation is very hard, but people are trying to do so. I think technically today we could only detect moons around giant planets that are as massive as terrestrial planets like the Earth, and 0 has been found. And then there are attempts to try to find moons for super Earths, if you don't know what to expect. And to my knowledge, there is no moon that has been. There are some which have been claimed and none which have been confirmed. And basically, the technique to find it is that if a planet has a moon, a significant moon around it, of course, it moves a little bit into the moon. And so when it transits in front of the star, it doesn't transit always at the same time, but you have some variations on the timing. So people look at these time transit variations with a lot of attention, but so far a lot of these time transit variations have been found, but they are due to companion planets and never to satellites. So for the moment, we are moonless for the extrasolar planets, but one day, better instruments, sure, something will come up.
Please join me in another round.
Thank you very much.